Welcome back. In this video, we're going to begin Chapter 8 on Statistical Thermodynamics. Now, in the previous chapters, we learned how to apply classical physics to understand the translational motion, the rotational motion, and the vibrational motion of atoms and molecules. We also learned how electrostatic interactions can lead to attractive and repulsive forces between atoms and molecules. And now what we want to do is to take that microscopic picture, the microscopic equations of motion describing atoms and molecules, and try to understand the emergent properties from a large collection of atoms and molecules, say 10 to the 23rd atoms and molecules, which lead to the kind of properties that we learned about in the last chapter on thermodynamics. So properties like the temperature or the pressure or the entropy of the collection. So we're going to try to do that in this chapter and learn about the approach of statistical thermodynamics as developed by people like Maxwell, Boltzmann, and Gibbs, and others. Okay. Now, when I think about this problem, I like to think about the analogy of a murmuration of starlings. So you can imagine, you've probably seen this before, when you have in the sky, you have this very large number of birds that are flying together, and they are following rules in their heads. Each bird is thinking, okay, I'm trying to stay with the flock. I don't want to avoid collisions. And in that process, they set up this system of rules that all of them are following, and it creates this emergent collective behavior where now we have properties like the shape and the volume of this large collection, which is not really something that each individual bird is thinking about. They just have following these simple rules based on what their local interactions are. And this is what I think about when I think about atoms and molecules coming together to get these emergent behaviors when you have large numbers of them. So we know, in the case of an atom or molecule, exactly what those rules are. Those rules are the physics that we've learned about previously, the classical physics, but also the quantum physics that we're about to learn, that tell us exactly how those atoms or molecules will move, translate, rotate, vibrate, and move through space based on their local interactions. And that set of rules will somehow lead to the emergent property of this collection, this 10 to the 23rd atoms and molecules, which are those properties that we learned about in thermodynamics. So to do that, we're going to look at Boltzmann's explanation of Clausius entropy from a microscopic point of view. Now, what Boltzmann knew was, of course, entropy always increased for any spontaneous process in an isolated system. So for an isolated non-equilibrium system, the state would always evolve to other macroscopic states that had higher and higher entropies until it reached equilibrium, where the entropy then would stop changing and it would be at its maximum value. Now, Boltzmann also knew that entropy must be related to probability. Now, we saw in the chapter on the kinetic theory of gases that a gas will, when it's at equilibrium, will have the Maxwell distribution of velocities or speeds. And we knew that if a gas started out at some non-equilibrium distribution of velocity, so say all of the molecules at exactly the same speeds, then through collisions, they would eventually evolve over time until they reach one of these distributions associated with their temperature. Similarly, if we started out with all the energy in one molecule in its velocity and all the other ones not moving at all, through collisions, it would eventually then equilibrate and come again to Maxwell's distribution at some given temperature. So the evolution from some initial entropy state to a final maximum entropy state at equilibrium was related to the probability distribution evolving over time until it reached Maxwell's molecular velocity or speed distribution. All right? Now, Boltzmann also realized that it wasn't just the distribution of speeds, probability distribution of speeds, but it also was related to the probability distribution of molecular coordinates, positions in space. For example, if you look at the Joule expansion, where we had a gas that expanded, an ideal gas that expanded into a vacuum, we know that that spontaneously occurs and we get an expansion where the entropy increases from this state to this state. But because this is an ideal gas, we know that the change in energy is zero, and so the change in temperature is zero. So that means that these two states have exactly the same Maxwell velocity distribution, probability distribution. So even though the entropy increased, the velocity distributions stayed exactly the same. But what did change was the distribution of positions. So the probability distribution of positions changed. So clearly, entropy was related to the probability distribution of molecular velocities and molecular positions. All right. So to try to make this work, Boltzmann introduced two concepts. That of the macrostate, which is the thermodynamic system state that's constrained by the n independent state functions, which we learned in the previous chapter. So that's the thermodynamic state. And then the microstate, which is some unique set of atomic position and momentum coordinates for the system whose equations and motions can be determined in principle from the Hamiltonian of the system. Now this microstate, you can imagine, is like some spreadsheet, which where you have for every individual atom, you would have its position and its velocity, and then you would have a list for every atom. You'd have some spreadsheet with position x, y, z, vx, vy, vz, and that spreadsheet would represent one microstate. And now what Boltzmann said was that for a given microstate, that there can be, for a given macrostate, there can be many microstates that would lead to the same macrostate. So at any instant, a macrostate corresponds to one of, I'll say, a mega possible microstates that are consistent with all the thermodynamic properties of the system. So what Boltzmann realized was that the more microstates that were responsible for a given macrostate, then the more probable that macrostate was. So in other words, more microstates for a macrostate increases its probability. And so an isolated, non-equilibrium system would evolve through some series of macrostates where each macrostate has an ever-increasing number of microstates associated with it as it moves towards the most probable macrostate, the one which has the maximum entropy. Okay. So in 1877, Boltzmann proposed then that there is a function, entropy function, that is dependent upon the number of microstates associated with a given macrostate. And what we needed then was what was the actual form of this entropy function, this function of the number of microstates. So we can actually get this function without doing much other than just realizing that entropy is an extensive property. So if I took two isolated subsystems, so say I have system A and system B, which has system A has an entropy A, SA, and system B has an entropy SB, then the total entropy of these two isolated systems, so remember rigid, adiabatic, impermeable walls, so we have two systems that are completely isolated, and the total entropy is just simply the sum of A's entropy plus B's entropy to give us the total entropy. So that means for an extensive property like entropy, the total entropy has to be equal to the entropy of A plus the entropy of B. And S now is this function of just the function of the number of microstates. Now, because these two states are isolated, it means that the number of microstates associated with the combined system, A and B, simply has to be the number of microstates associated with A times the number of microstates associated with B. That gives us the total number of microstates. So if I plug that into our above expression for just the extensivity of entropy, then we get this equation here. And this equation is a functional equation. What we need is to figure out what function S gives us this type of behavior. And it turns out a simple function that will give us this behavior is just the log of the number of microstates. So this function solves this functional equation. And Boltzmann needs a proportionality constant here, which we now call the Boltzmann constant, that gives us the right units for entropy. So it's the log of the number of microstates times the Boltzmann constants give us the entropy of that system with that set of microstates, with that number of microstates. Okay, so a macrostate with this number of microstates has this entropy. And that means we can also then calculate the change in the entropy. So by just saying S final minus S initial, so that would just be this equation for the Kb times the log of the final number of microstates minus Kb times the log of the initial number of microstates. And remember our rules for logs. This gives us Kb times the log of the ratio of the number of microstates. So let's apply Boltzmann's equation to calculate the change in entropy for a thermodynamic process. And specifically, we're going to calculate the case of Joule expansion of an ideal gas. So remember that example will involve a gas that's confined to 1/2 of the container's volume and the other half is a vacuum, and we let the gas expand into the vacuum in a spontaneous process, an irreversible process. The entropy increases from the original state to the final state, and in that process we find that the number of microstates associated with the original macrostate is smaller than the number of microstates associated with the final macrostate. So our goal now is to figure out how to calculate the number of microstates here and the number of microstates there. Now, we're going to assume that the macrostates are described by 3 thermodynamic state functions. So we're going to assume the total energy, the total volume, and the total number of atoms or molecules are the 3 macroscopic thermodynamic state functions that we're going to describe our 2 macrostates here. And now to count the microstates, we need to know how many sets of momentum and positions are compatible with the initial and the final macrostate. Now for an ideal gas, we know that there are no interactions between the atoms and molecules in the gas phase. So that was one of the classic assumption of the ideal gas. So that means that the energy of an ideal gas is purely kinetic. And that means that the energy depends only on momentum. So if it was a real gas, there would be attractive and repulsive forces between the atoms and molecules, and the energy would depend not only on the momentum, but also on the positions of the atoms, how close or how far they were from each other. But in an ideal gas, there's no interactions between molecules. The energy is purely kinetic. And in that case, then the number of ways in which you choose the position coordinates is independent of the number of ways you can choose the momentum coordinates, and that means that we can factor the number of microstates associated with a given macrostate of an ideal gas into the product of the number of microstates with the momentum that's consistent with the macrostate of the gas times the number of microstates associated with the different positions that are consistent with the macrostate of the gas, and that product gives us the number of microstates associated with that particular macrostate. So for an ideal gas, this in 2 states, the initial and the final states, have exactly the same number of momentum microstates associated with them. That's because they depend purely on the kinetic energy, and that is the same in both of these cases. They have the same speed distributions, the same Maxwell's distribution, same temperature before and after. What's changed is the probability distribution of their positions. The number of microstates associated with positions has changed, has increased from here to here. And so that's the quantity that we need to calculate. So how are we going to calculate the number of position microstates for the initial and the final macrostate? Well, the way we're going to do that is we're going to discretize space. So what we're going to do is we're going to imagine that we take the total volume of the sample and we're going to divide it up into tiny little cubes. So in 2D, you might imagine dividing up 2D space into little pixels, and then in each pixel, you might imagine your 2-dimensional atom or molecule might be in each one of these different pixels. But now in 3D, we're going to divide it up into voxels, and these voxels will have a volume, will have lowercase v here, and we're going to choose this v, this voxel volume, to be large enough that it's bigger than the size of one molecule, but small enough so that the total volume divided by the number of voxels is much greater than the number of atoms or molecules that we have, okay? So that means that we can assume that each voxel is either empty or at most is occupied by one molecule, okay? And we can assume then that the voxels have equal probability of lowercase v, voxel volume over total volume, to be occupied by a molecule. So there's no difference in the probability of the molecule being here or being there or being there. They all have the same probability, so that probability is just the voxel volume divided by the total volume. And the number of ways then that a single molecule could be distributed inside our voxylated total volume is just total volume divided by V. It can be in any one of these possible voxels, okay? And the number of voxels is just this total volume divided by V here. Now, when it comes to distributing two molecules, you would think that that's just the total volume divided by the voxel volume squared. But actually, it turns out that that is going to have to be divided by 2 factorial. So it's going to be reduced from what we would imagine sort of classically. And the reason we have to divide by 2 factorial is because of the quantum mechanical uncertainty principle, which is something we have to get to in a later chapter. But it turns out that if you had 2 atoms, say 2 helium atoms, you can't really distinguish those 2 atoms. So when they collide, you can't say that this is helium A and helium B. After the collision, you can't say that helium A went over here and helium B went over there. Once the uncertainty principle comes into play, we can't distinguish after the collision which one is which before and after. So we'll come back to this later, but the upshot of that is that because of that indistinguishability, we have to make sure that we don't overcount. We can't count possibilities that we can't actually know. So that means that voxel I with molecule A and voxel J with molecule B, it has to be considered to be identical to voxel I with A and voxel J with voxel I with B and voxel J with A. So that counts as only 1 microstate. So in order to do this with n atoms or molecules, then we have to divide by n factorial to avoid overcounting. So in other words, V over capital, the total volume over the voxel volume to the nth power divided by n factorial is the true number of microstates. And it's only when you have localized particles, when molecules or atoms are fixed in a lattice, that you can drop the division by n factorial. But in the case of a gas where the molecules can collide and the uncertainty principle comes into play because we never know which one's coming out in which direction from that collision volume, that we have to divide by the n factorial to avoid overcounting our number of microstates. And again, we'll come back to the reasons for this after we get into quantum mechanics. So for now, we're just going to add this in to make sure we get the right answer that accounts for that quantum behavior. So that means then that our position, the number of microstates that we have for the position, is the total volume divided by the voxel volume raised to the nth power. And now we include this division by 1 over n factorial to take into account this quantum behavior for indistinguishability. And now with this expression, we can go back, I'll just write back here again. We can go back to this expression and calculate the ratio of the number of microstates for before final and over initial. Sorry, go the wrong direction here. And calculate this ratio, which is the product of number of momentum microstates times number of position microstates final over the number of momentum microstates times number of position microstates initial. And these actually are the same. The number of momentum microstates is the same for initial and final, so that's going to cancel out, and we're just going to have the ratio of these 2 terms, which is just the ratio of this expression substituted here and there, which gives us this expression here, which is the V final over V initial raised to the nth power. And that's our calculation for the ratio here. Now we simply have left to take the log of that ratio and multiply it times the Boltzmann constant, and that gives us this expression here. Using the rule for logs, we can move this n down over here, and we get this expression for the change in the entropy. And the number of atoms or number of molecules is just simply the number of moles, the amount, times Avogadro's number. So we'll just substitute n times Avogadro's number for capital N here, and that gives us this expression here, which we can now compare to the result from the previous chapter for the Joule expansion of an ideal gas, which was this expression here. So looking at this and looking at this, we see now that they give agreement for the behavior with the log of the V final over V initial, and we also identify that Avogadro's number times the Boltzmann constant is just the gas constant, as you see here, and that's given by this value there. All right. So we've done this very simple calculation using Boltzmann's expression, and it agrees with what we get from using Clausius' definition of entropy. So we can also look at another example here. So we're going to derive the ideal gas equation of state using Boltzmann's equation. And to do this, we're going to use what's called the Stirling approximation, which tells us that for large n, we can approximate the log of n factorial is approximately equal to n times the log of n minus n, which can be actually rewritten as n times the log of n over e, which is Euler's constant here. So we'll take the result from the previous case and we'll write down the product of the momentum and position number of microstates, and we'll put in our value that we came up, expression we came up for the position number of microstates here. And if we substitute this in to the expression for the absolute entropy, then you can see it factors into these three terms here. And now this is the absolute entropy with this picture, and you can see that depends on actually the voxel volume. So there's something arbitrary about this from the classical point of view, and we'll come back to that later. But we can now go back to our thermodynamics chapter, and we know that the pressure over temperature is equal to the partial derivative of the entropy with respect to volume at constant energy and number of moles, or number of atoms or molecules. So if we take that relationship from thermodynamics, apply it to this equation here, then when we take the derivative with respect to volume, actually this doesn't depend on volume, that doesn't depend on volume, only that depends on volume, and that ends up giving us this expression here. And if I then use the definition from our previous slide here for the relationship between Boltzmann constant and the gas constant, then you can see that becomes R nR over V, and that's equal to P over T. So together we get PV equals nRT. So what have we done? We've just derived the ideal gas equation, the equation of state for ideal gases, from Boltzmann's expression for the entropy, all right, by counting the number of microstates. So we derive from first principles the ideal gas law here in a statistical thermodynamics manner. Okay. Now, if we can't count the position of the microstates separately, like we did in this ideal gas case, then we need to find a more general approach. Okay, so this approach that I showed you now was kind of very specific to the ideal gas case, but just to illustrate the concept so you understand what's going on. We need to dive into a more sophisticated treatment to understand how to calculate the number of microstates in the more general case when we can't separate position and momentum like that easily, when the energy depends on both of those position and momentum coordinates. All right. So that'll take us to the next section on how to count microstates in the most general case, which is counting microstates in phase space.